Hi, my name is Ronnie and I work as a consultant at the Danish Technological Institute. In this course, we'll take a deep dive into the 3D printing technology known as material jetting. Looking at the agenda for this course, first we're going to look at what material jetting is, then we're going to look at the pros and cons of the technology, we're going to dive into the design possibilities and the design guidelines, we're going to look at the materials that you can print in, what we can actually print, then we'll look at health, safety and environment, we'll look at the printing process itself and the post-processing, and finally there are some links and references for further reading. Looking at this chart of the 7 additive manufacturing technologies, we're in the category of material jetting, and here we have 3 sub-technologies. We have material jetting, or MJ, we have nanoparticle jetting, NPJ, and finally we have drop-on-demand, DOD. If we look at the ISO standard, we can see that the most common material is polymer, the fusion state is chemical reaction bonding, and the material feedstock is a liquid or a resin in this case. The material distribution happens through a print head, and the basic AM principle is light reactive photopolymer curing. As we saw before, the process category is material jetting. Let's start by looking at what material jetting is. As mentioned before, we have 3 different types of material jetting. The most common one is also called material jetting, then we have nanoparticle jetting, and we have drop-on-demand. I'll cover these individually in the next couple of slides. Let's start by looking at drop-on-demand. Here the printers have 2 print jets, one for support and one for depositing the build material. The print jet follow a predetermined set path to jet the material onto the platform. Generally, this technology is only used for production of casting patterns, and that means you typically print in wax-like materials. There's no curing use for this technology, but instead you mill the part to form when you're finished. Next up is nanoparticle jetting. Here you jet a liquid of nanoparticles of metal or ceramic, and the print material and the support material are jetted simultaneously. The curing happens with heat, so there's actually a very high temperature inside the build envelope of up to 250 degrees. This high temperature also helps vaporize the resin, so you have behind the porous metal part. Therefore, the part needs to be sintered after printing. This technology is patented by X-Jet, so it's still a technology for the future. Finally, we have material jetting. Here you jet tiny drops of material across the build platform, and the print head will both print and solidify using UV light. This technology requires support, which is printed simultaneously. The benefit of this technology is that you're able to print in multi-material and full color, and the optimal print temperature is around 30 to 60 degrees. Since material jetting is the most common of these technologies, we'll focus on that technology going forward. A material jetting printer consists of 5 main components, as we can see in the schematic below. First, we have the material container, then we have the UV light for curing, we have the inkjet print heads, then we have the build platform that you print on, and finally we have the elevator that lowers the platform. If we look at the process flow for material jetting, you start by inserting resin and a build platform. Then you jet resin in one layer and you solidify that layer using UV light. Then you move the platform down and continue this process until you have the finished part. Then you take the part out of the printer and remove the support. When printing with material jetting, we have 2 settings for the surface finish, either glossy or matte. With glossy, you get a smooth and shiny surface where you have no support, and you reduce the material usage. The downside is that you get a non-uniform part and you get some rounding of sharp edges and corners on the top surface. On the other hand, you have the matte surface finish where you get a higher accuracy of the part and a more uniform finish. The downsides are that you have additional material usage, you have additional cleaning time, and you get a softer surface finish, and by using more material you also have additional cost. Material jetting printers come in different sizes and prices. On the left we see an example of a desktop printer, but these are not very common. And then on the right you have an example of an industrial printer. The main difference between the 2 types of printers is the size of the parts that you can print, but of course also the price of the printer. And an industrial printer will be way more expensive. In this video we see how a material jetting printer is working. We see the print head jetting material onto the platform and curing it at the same time, and this process continues until we have the final part. Next up, we'll look at the pros and cons of the material jetting technology. With additive manufacturing, we typically distinguish between visual appearance and functionality. Material jetting gives us parts with visual appearance mainly. You can get a very smooth surface, you can get transparent parts, and you can get parts in full color. The visual appearance is also supported by very high tolerances, and you can get parts with rubber-like materials. But the parts are very fragile, so the functionality is very limited. The main benefit of material jetting is the very high surface finish and accuracy. Material jetting is actually considered the most accurate form of 3D printing, and the dimensional tolerance is 0.1 millimeters, or sometimes as low as plus minus 0.02 millimeters. Due to the low temperature during printing, warping and shrinking is also very uncommon. Another benefit is the possibility of multi-material printing. This can happen in different ways. For example, you can have a mixed tray where you have separate parts from different material on the same build platform. You can also have digital materials where you combine 2 or even 3 resins. And you can have mixed parts that remove the need for assembly of components. And mixed parts also eliminates the downtime for material changeovers. Finally, it's possible to have full color printing. Another benefit are the homogeneous properties. This is because we cure 3 layers deep during the process. So we add the first layer and we cure it to 60%. Then we add the second layer. We cure this layer to 60%, and the first layer that we added is now cured to 95%. Then we add a third layer, we cure this layer to 60%, the second layer is cured to 95%, and then the third layer, which is actually the first layer that we added, is now cured to 100%. The benefit of this process is that you get better layer bonding, you get reduced porosity, and you get more homogeneous properties regardless of the orientation of the part. One of the downsides of material jetting is that it's rather expensive. The industrial printers can be very expensive, but the material prices are also quite high compared to other technologies. The support requirements of material jetting can be both an upside and a downside. The advantage is that the support is printed in different material. It's easily removed due to dissolvable support material with light agitation, and the surfaces show no indication of the support, and orientation of the part is more flexible than other methods. On the downside, support is printed solid and you're using more material, and this of course increases the cost of the part. The main disadvantage of material jetting is the material properties, because the parts are better to look at than they are to use. The parts are very brittle, you have a problem with loss of mechanical properties over time due to degradation in sunlight, and for that reason it's not recommended to use the parts outdoors. You also have very poor mechanical properties, and the parts degrade over time, and you get low elongation at break. Summing up on the pros and cons, you get a very high surface finish, you get fine details, a high accuracy, you get homogeneous properties, multi-material properties, you get a high level of design freedom, and you can use dissolvable support material. On the downside, the parts are very brittle, you have poor material properties, the parts are UV sensitive, you're printing with solid supports, which gives you a higher material usage, and the technology is rather expensive. Now it's time to look at the design possibilities with material jetting. One of the possibilities is to have multi-material printing. As already mentioned, we can have different colors in one part, we can have different materials, for example rigid and flexible, and we can eliminate the need for assembly. Another possibility is to print elastomers, which are flexible rubber-like materials. So as we see in the picture below, you could for example print a prototype of a shoe with realistic material properties. This leads us to another possibility, which is realistic designs and prototypes. You get very realistic prints with high accuracy, and you have an enormous design freedom because support is printed solid and because you can orient the part any which way you want. You can also have more design iterations in a shorter amount of time, so you'll be able to identify errors in a prototype at a much earlier stage than you would with another technology. Looking at the general design possibilities, you have a very small feature size, you get high resolution, high accuracy, it's great for prototypes and visual mock-ups. You can also print in multi-material or multi-color, and it's possible to print elastomers, which are flexible rubber-like materials. To get the best results, we also have some design guidelines, and we're going to look at them here. Hubs has made this overview that show the different design rules for material jetting. On the next few slides, we're going to look at support and overhangs, embossed and engraved details, holes, minimum features, pin diameter, and tolerances. The standard tolerances for material jetting are plus minus 0.1 mm, but it depends on the size of the part. There are some features and designs that can affect tolerances negatively. These are large flat surfaces where some warping can occur via shrinkage. As mentioned earlier, this is not the biggest issue with this technology because we're printing at a very low temperature. Another feature that you should avoid is wall thicknesses below 1 mm. When you have overhangs, you always need support. You should be aware that the support is printed solid, so you use more material than you do with other technologies. But you can print the support in different material, and it's possible to minimize the amount of support with the correct orientation. If we look at minimum features, the magical number is 0.5. That's because the minimum pin diameter is 0.5 mm. The minimum size of a feature is also 0.5 mm. Holes should have a diameter of at least 0.5 mm. And for embossed and engraved details, the height, depth and width should also be, you guessed it, 0.5 mm. The reason why we have these design guidelines is to ensure that we get the best possible result and that what we design is also what we get out of the printer in the end. This shouldn't keep you from trying to experiment and challenge the boundaries, but if you want to make sure to get a perfect result, you should stay within these guidelines. Let's take a look at the different materials that we can print in with material jetting. To get us started, Stratasys has made this video on the evolution of materials, which gives us a bit of an overview. As we saw in the video, we get a wide range of materials. For example, we can get photopolymers and casting wax. We can have materials that are designed for simulating traditional material, and we can have different colors and properties. We should be aware that material jetting requires material with a low viscosity. And in general, photopolymer resins gives us a nice finish. It also gives us brittle parts, and it gives us aesthetics over function. As we can see below, we get many different materials and characteristics with material jetting. Common to all these materials are that they are quite brittle, but you also get some advantages. For instance, you can have flexible materials where you can customize the hardness. You can have materials that simulate the properties of other materials, for instance, polypropylene or ABS. And you can have transparent materials where you get an even glass-like appearance. One example of a material is digital ABS+. This material is designed to simulate standard ABS plastics. It's temperature resistant up to 70 degrees, and you get toughness, impact resistance, and shock absorption. Now it's time to look at some of the things that we can print with material jetting. First of all, material jetting is often used for full color visual prototypes. Here you can have very detailed visual prototypes, and this is often used in, for instance, surgery, where surgeons have anatomic models for surgery training so they can prepare before an operation by looking at a model that is an exact replica of what the patient looks like inside. Another popular use is for transparent materials. This is often used in the automotive industry, for instance by Audi, who uses full-color multi-material for their prototypes. Another use for material jetting is injection mold-like prototypes. Here, the technology is used to verify injection molded designs, and you get a very high level of detail and a smooth surface finish. With this technology, the designers are able to check their designs in terms of clearance, fit, and assembly, and they can do that because of the very high accuracy of the technology. Even though material jetting is a quite expensive technology, it's still a very quick and low cost compared to actual injection molding. Speaking of injection molds, material jetting is also used for injection mold prototypes because of the high level of detail and the smooth surfaces. It can also be used for low-run injection molds if you have less than 100 parts. Material jetting is also used when you want to have a mixed tray or a mixed build platform. As we've heard previously, you can have multi-material, so you can separate parts from different material on the same build platform. All parts, regardless of the material, get a very high accuracy and a smooth surface. The last use case that we'll focus on here are dental applications. Here, material jetting is mainly used for realistic training models, and you can have different applications and materials, and you are able to print perfect shapes and gum-like textures. Let's look at the safety aspects of material jetting. Before working with material jetting, you should always read the safety data sheet and other manuals before you start. In addition, you should always have the necessary safety equipment, which includes ventilation, a mask, safety glasses, gloves, and the proper work clothes. When printing with photopolymer resin, you should be aware that uncured resin is classified as hazardous industrial waste. You should also make sure that the printer area has adequate ventilation, and you should clean parts according to the material specification. Note that material jetting printed parts can be approved for use with medical application on the human body, but it depends on the material that you use. We looked at the printing process itself in a previous chapter, so now we'll look at the steps that come before and after the actual printing. The first step is that we need to prepare the parts that we want to print. We do that by opening the parts in the job preparation program. Here we can see an example of such a program, which is from GrabCAD Print. Next up, we need to orient and place our parts on the platform. And the goal is to orient the parts so we minimize the print time. There are two rules to optimize the print time and the print quality. The first rule is the tall left rule, and that means that you place tall items on the left of the platform instead of in the middle, as you can see in the picture below. You do this to avoid unnecessary travel of the printhead. The second rule is the single pass rule, and this is that you keep small parts within one width of the printhead, as you can see in the images in the bottom right corner. Regarding orientation, there are two more things to be aware of. First, you want to have as low an orientation as possible, so instead of having parts standing up, you want to have them lying down. Secondly, you want to place parts in the same pass to save time. As we can see in the pictures below, we don't add much time even though we add 4 parts in the same pass. But if we spread the parts across 2 passes, then we actually add time even though we decrease the number of parts. Once we've oriented our parts, we need to choose the surface finish, and here we can choose between glossy or matte. When you have support material, this results in a matte finish, and you use the matte finish when you want to have a uniform surface all around the part. If you look in the table below, you can see some of the typical uses for either glossy or matte. If we look at the pictures to the right, we have a part that needs support. The top picture shows the part partly covered in support, and then if we go below, we can see that the support has now been removed, and the top part is glossy and the bottom part is matte. If we go down a further step, we can see that now the entire part is covered in support. And then below, we see that the support has been removed, and now, because the part was entirely covered in support, the entire part is matte. Now it's time to add support to our print job. And here we can choose between 3 different settings. We can use default, smart, or wide. Below we can see examples of the different types of support. And what we can see is that smart support typically uses less support material than the default support. The wide support is used when you have, for example, a tall, thin structure that you need to support all the way up. The support is usually generated automatically by the job preparation program. Before printing, we also need to scale our print job. In rare cases, the parts may shrink when the material is cured. In such cases, the model must be scaled, but shrinking will depend on the material that is used. Shrinking is rarely a big issue with material jetting since the printing process isn't using high temperatures, unless it's a nanoparticle printer. Now it's time to prepare the printer itself. Here we start by adding or changing a cartridge with photopolymer resin according to the print job. Then we clean and prepare the print platform, we upload the print job to the printer, and then it's just a matter of pressing print. Now we fast forward to after the print job, and here we start by removing the parts from the platform. The parts are removed with a spatula like the one you see to the right, and you should be careful not to damage the platform or the printed part. Once the parts are removed from the platform, we need to remove support from the parts. The support is removed by dissolving it or by manually removing it and washing the parts by hand. You can use waterjet for faster support removal, and there are also cleaning stations available for medium-sized parts. Before we have the finished part in our hand, we need some post-processing, and that's what we're going to look at here. In general, you need very limited post-processing for material jetting, and that's because the parts already have a smooth surface. The support marks are almost non-existing, you have great tolerances, and it's possible to print in different colors. However, it is still possible to improve the parts after printing. For instance, you can do that by sanding them, you can use dyeing or painting, you can use coating, or you can photo bleach for clear materials. I'll cover these processes individually in the next couple of slides. First, we have sanding. Sanding and polishing can be useful if you want to have very smooth surfaces. In this case, you almost always use wet sanding with a grit size of 320, and this is the case if you want to paint the parts afterwards. Next, we have dyeing and painting. Dyeing is mostly used on clear and translucent parts to change the appearance without losing the transparency. On the other hand, painting the parts can help protect them against overcuring by UV light. It's also possible to use coating. A clear coat can be applied to improve the wear resistance, and coating can also help increase the lifespan of the part. A metal coating can also be applied for decorative reasons or if you want to achieve better properties. Finally, we have photo bleaching, which is used to improve transparency. Photo bleaching is used for clear materials, and you can see the result in the pictures to the right, where the top one is before photo bleaching and below you have after photo bleaching. Finally, we have some links and references for further reading if you want to learn more about material jetting or additive manufacturing in general. On this first slide, we have some general links for more knowledge about additive manufacturing. And on this second slide, we have some more specific links about material jetting. That brings us to the end of this course. I hope it was helpful, and thank you for watching.